it's not particularly interesting. We need to be able to do animations that are far more complicated than this. And Unreal has many great built-in systems to do this. The main one being the animation blueprint, which is a blueprint, obviously, so we're not going to be doing this in C++ because animations just make sense to be done in blueprint. And the main point of the animation blueprint is to bring together all that animation logic and allow us to kind of blend and merge and switch between animations such that our game logic can then drive that animation blueprint. So without further ado, let's try and create an animation blueprint. So in the content browser, either add new or right click, and we're going to go to animation and select animation blueprint here. And you'll see right off the bat, it is asking us to maybe have a parent class. We don't need a parent class, we can just use the default, but it does need a skeleton. Because like the animations, like the skeletal meshes, they both rely on the skeleton, so does the animation blueprint, which means that then it can use all the animations of that skeleton and it can be used on any of the meshes that relate to that skeleton. Now, obviously, we want the Wraith skeleton here, so let's go ahead and select that and click OK, and that's going to go ahead and create an animation blueprint based off of the Wraith skeleton. And then for naming convention, we start with ABP underscore, and I'm going to call this the just shooter character, basically, because we've got that different prefix. I think it's clear enough. It's the animation blueprint for the shooter character. So if we go ahead and open up that animation blueprint and dock it to our main window, then we're going to see an animation blueprint editor, which in many ways looks similar to your usual blueprint editor. It's got this main graph area in the middle, but in some ways it's different. So we've got the graph area, that's similar. This is a slightly different graph to what we're used to. It's called the anim graph. You can see there's also an event graph, just like your regular blueprint. They have an event graph, but there's also something called an anim graph. We'll get to that in a second. There's a details pane, which gives you details about the animation blueprint. So the class itself, you've got the details on that. Notice we don't have any components against an animation blueprint. That's one difference to note already. We've got this anim preview editor, which allows us to do some stuff with this preview window over here. Why then? not closer to each other by default, I don't know. Asset browser, just like on the animations, allows us to look through animations easily, bring them in to our editor. And here at the top right again, same as animations and meshes, we have this view that allows us to quickly switch between the skeleton, the mesh, and the animations, and the blueprints that all rely upon that same skeleton. Then over in the bottom left, we've got that My Blueprint pane, which is very much the same as My Blueprints on your standard blueprint. You've got your functions, your variables, macros, that sort of stuff is the same. What's different, oh yeah, we've got the graphs as well, that's also the same, but what's different is this animation graphs and animation layers. Now we're not really going to touch upon animation layers, that's a bit more of an advanced feature that we don't need, but the graph, that is what is very important indeed, because the graph is kind of like blueprints, except we have no execution node. All we've got is the data that flows through the graph. And what does flow through the graph? Well, basically, we're trying to get to this output pose, this output animation pose that we should model our character into. And we do that by connecting up lots of different nodes to this result node, and flowing through that, we end up getting the data that is our output. One simple output that we can go with is, for example, just dragging in an animation into this anim graph, and you can see that it creates a node. And it has an output pin, which is an animation pose, and if we drag that pose onto the output pose and hit compile, you can see that it's just going to show in our preview what this animation blueprint does. It essentially just plays this ability animation. And that's pretty much what we're doing at the moment, except now we put an extra layer in between. You know, we're putting a blueprint in instead of just playing the animation directly. That's not particularly useful in and of itself. But the different kinds of operations we can do on these poses, now that is useful. If we right click in the anim graph, you can see there's a lot of stuff going on here. I want to search for something called a blend, and there's a few different things in here. Let's see if I can find the most useful one. We want at the top, there is a few here. I think blend bone by channel, blend multi. We want just the standard blend node. Let's bring that in. And you can see here we've got a value, we've got 2 input poses and 1 output pose. So what we can do is we can drag in 2 different animations. We can stick, this one's an additive animation, I don't want to bring that in, that's going to confuse us. Let's use some animations that we might actually use. So we were looking at the forward movement, we've got jog. Jog might be more what we want rather than walking. So let's have a little look at our jog forward. That might be one thing that we can blend. And then the other thing we could blend, looking at output pose, and find the most useful one. We want at the top, there is a few here. I think blend bone by channel, blend multi. We want just the standard blend node. bring that in. And can see here we've got a value, we've got 2 input poses and 1 output pose. So what we can do is we can drag in 2 different animations. We can stick, this one's an additive animation, I don't want to bring that in, that's going to confuse us. Let's use some animations that we might actually use. So we were looking at the forward movement, we've got jog. Jog might be more what we want rather than walking. So let's have a little look at our jog forward. That might be one thing that we can blend. And then the other thing we could blend is a jog back. So let's just look for jog. And we've got jog BWD, which I think stands for backward, forward, backwards. Let's bring those into our blend node and then output. Them and see what the result's going to be when I hit compile. You can see I'm jogging forward. If I stick my alpha over to 1 and then recompile, you can see that now I'm jogging backwards, and you can see also as the preview runs, you can see which nodes, where the data is flowing basically from the jog backwards through the blend node, and there's nothing coming through that pin A because alpha blends between the two. Now I can do a 0.5 on the alpha or anywhere in between, and that's going to try and play both of the animations and layer them on top of each other, half of both of them. And obviously when you're dealing with jogging forward and backwards at the same time, that starts to look a little bit funny, doesn't it? So what I'm going to do here is I'm going to remove the jog backwards and put in an idle animation instead. So where do we have idle? I'm going to select this idle non-combat and bring that in here. So that now what should happen is if we're at 50%, it's kind of doing this idle non-combat, half of that, and then half of the jog. Whereas if I put it at 1, it's going to do 100% idle, 0, it's going to do 100% jog. Now, this is not ideal, the fact that I keep changing this alpha, having to hit recompile. So what we can do is we can add in a variable to our blueprint. It needs to be a float. So we can go ahead and change the variable type in the details pane to float. And I'm going to change this to blend amount. So, and then we can drag that in, so we can drag in any variables from our blueprint into the anim graph and hook it up to some of the pins, hit compile, and now if we go back to our anim preview editor, you can see that it's showing up these variables like that we've created over here, the blend amount. And that means that now if I can just shift that at runtime, I can see and preview what would be happening. And then basically what's going to happen is our game is going to drive these variables in the animation blueprint to get the right sort of animation at any particular point during playing. That's what we're going to deal with a little bit later on in this section, but for now we're going to try and get this animation looking right when we have the right sort of variables in here. So it's time for a bit of a challenge. See if you can get set up with an animation blueprint and play around with the anim graph. So I'd like you to add another blend. We're going to add them up in sequence. So first you're going to do one blend, its output is going to go into the input of the next blend. Then select an animation that makes sense, such maybe as moving right or left, and add some variables that also make sense so that you can tweak them and look at the preview and you can blend between all of the animations, the idle, the moving forward, and your animation of choice, whether it's moving left or right, something like that. Pause the video and have a go. Just play with these blends, see if you can make sense of the anim graph. Hey, welcome back. So hopefully you've had a little go. We're going to go and add in another blend node. So search for blend and then scroll up for some reason. This might be to do with my screen scaling. go to the blend and bring across, let's see, these idle animations. What do I want to do? I think I want to have it move left. So I'm going to look in my asset browser for jogging, and we're going to look for a jogging left animation. Now, by the way, I do know that blends are not the ideal way to do this. In the next lecture, we're going to look at a better way of doing this, which is going to be to use something called a blend space, which automatically allows us to blend movement animations in a very nice way. But we're doing this just to get the idea of the anim graph before we dive into more complicated things. So we're going to blend between, let's see, left and forward, I think. So left here, and we're going to copy, cut, move forward over to B here. And then we're going to patch that in, the output of the blend, into the input of the next blend, the one that does idle or not. Does this actually make sense? Let's think about the variables. What should the variables be called? I'm going to have one which is called forward, just forward, it's quite simple, and one which is called right or left, because we're choosing a left animation. It's also going to be float. So one of the blends needs to choose between forward and not moving, so that's going to be, let's try and make that first blend. We'll hook in the idle non-combat to A, so that at 0 alpha it is going to be not moving. At 1, where forward is 1, let's hook up that forward variable to alpha. At 1 it's going to move forward. Then we're going to bring that in to 0 of moving left. Hook that left variable up, 0 of moving left. And at 1 of moving left we're going to hook up B. Basically we're going to hook up the jog left. So if we compile that, it's a little bit scatterbrained, but hopefully you get the idea. If we go over to the anim preview editor and we move forward, you can see that we start jogging. We accept that. And if we move left, you can see that we start moving left. And crucially, if we do both, move left and start jogging, we should see a blend a little bit of both. Here we've got that forward being blended. If I need to have a little bit less of the left, 50% of the left, you can see I'm kind of moving. It's a weird looking animation. It's not blending it particularly well, but you can see that it's playing both the jog left and the jog forward. Now, as I said, we're going to leave these variables more or less intact, but we're going to change the mechanism by which we actually do the blending to make more sense and use more of those animations that we're seeing in the asset browser for jogging forward, jogging backwards, jogging left, etc. But that's all the subject of the next lecture. This one we have covered more or less the animation blueprints and how the anim graph works and why we have it there in the first place. So I'll see you in the next lecture for more animations. Hello and welcome. We're going to look at this great thing called a blend space in this lecture and how it allows us to smoothly move between different types of movement. Let's dive in and see it in action. So as we've said, these blend nodes are not a very good way of doing animation with at least locomotion animation, which is what we call this moving around animation. So what is? Well, fortunately in Unreal we have got an asset specifically designed for this kind of thing. When we want to blend between things in a two-dimensional space, it's called a 2D blend space. So what we're going to do is go over to our content browser and create one of these, and then I will take you over what it is, what it means, and what's the point. Go to add new, animation, and blend space. You can see there's also a variant that is one-dimensional. We're going to be going for the two-dimensional one. Reason being, we've got two dimensions which are going to be the forward-backwards dimension and the left-right dimension. So let's go for that. We've got to pick a skeleton that needs to be based off. That's going to be the wraith skeleton. And then the prefix is going to be BS underscore, and we're going to call it locomotion because it's all about moving our player around. So we open up our locomotion asset, and you can see that right off the bat it is a new editor yet again. It's actually creating a new type of animation. It's making animation out of other animations, but it's still sort of an animation. animation, and you can see that's displayed in the top right. We've got details for this asset, which are currently empty. We've got asset details over on the left. I'm not quite sure what the difference is there. I think the details over on the right might be to do with the animation selected. We've got a skeleton tree if you need it. But the main area is this middle one. We've got a viewport, and underneath it we have got this two-dimensional graph. And what this is saying is that we could put a value along the bottom, which might be our left, right, and a value along the left, which is going to be up and down perhaps. And then this green dot we can move around to any position on here. And what we'd like to happen is if I put it over to the top right, then we move forward and to the right at top velocity. If I put it over to the left, we move forward and left, or down to the bottom, we go backwards and left at full velocity, and anywhere in between. So that's the idea here. We want to basically be able to move between these blend spaces, and we want to be able to choose an animation and blend between it. So what actually happens? Let's see. If we can bring in a walk animation, I'm going to bring in a walk left animation, a walk right animation over to the right here, and then we've got forward and backwards. So let's put a backwards down here and a forward up here. And then you can move this little green dot, and you can see that it starts moving forward if I go up, it starts moving backwards if I go down, and going over to the left and to the right, it is essentially working as we would expect it to. The only thing that's looking a little bit weird is here in the middle, where we're kind of stomping on the spot because we don't have an idle animation. So we do need to introduce that. But before we do any of that, we've got these axes that are labeled as none. That's not particularly useful. What should their labels be? How do we change them? Let's have a look. We need to go over into our assets details here, and there are axes settings. So we've got our horizontal axis. That's going to be our left and right. So I'm just going to call this right. And its minimum value I'm going to put as -1, so going at -1 speed, and maximum as +1 speed. We're going to update these based on the actual values of the animations later on in the game. Now the vertical axis I can go and edit to be forward, and we're going to go between -1 and 1 here as well, so -1 to 1. You can also select the number of divisions that you want in the grid. Here we've got 4 divisions, but you could increase that if you want to put animations at different intervals, and we'll be doing that later on as well. So this is interesting. We've got our forward and our left and right, and I appear to have lost my little green nubbin there, so I'm going to just close down the asset, hopefully bring it back up and see. Yeah, there you go. The green nubbin is back. So now I can go back forwards, I can go backwards, left and right. Now we want this to actually be more complete, so that we can run backwards, so that we can run forwards, we can walk forwards, we can run left, we can run right, and we can have an idle animation in the middle. Now if we were to do that, we would find that we end up with a kind of cross formation, and at these points in between it wouldn't really know or behave very well. So what we're actually going to do is tweak these axes so that we get something a little bit different. Instead of having right and forward, we're going to end up with having the angle and having the speed as the other dimension. So that if we want to go backwards, you need to turn around 180 degrees on your angle and go at full speed. So what should these values be? Well, these should be a little bit different. We're going to go from -180 to +180 on the angle, full circle. And speed-wise, we're going to go from 0 to, I don't know, let's say 100 for now. And then how would we be laying out these different animations that we've just laid out in one way, we can lay them out differently. We've got a backwards animation that's going to go at full speed at -180. It's also going to go at full speed at +180. So that backwards animation needs to be in 2 places. So let's find our walk for backwards and put it in this other place as well. Now our walking right, that's going to go, actually that's a walking left animation, that should go over at our -180. Our walking right should go over at our +180, and our full walk should go there in the middle. And as I said, we do need some sort of idle animation, so let's go and look for the idle combat animation. Has the gun raised, I believe. So we go and put idle combat, and we're going to put idle combat all the way along the bottom here in each one of these slots to make the blend super clear that no matter what angle you're at, if you're idle, you want to be stationary. So let's try that. I can now move my angle. You can see I start moving at a different angle depending on where I bring that green nub in. And if I come down, you can see it reduces my speed until I am idle. So that's what it's doing no matter where I start, and I come up and it starts to move me over to the left or to the right or wherever I am. It is kind of making sense. So my challenge to you is to complete this blend space. We're going to do that by adding jog combat animations so that we can go faster as well as slower. And where should they go in our scheme? Whereabouts should they be put on this blend space? Pause the video and have a go at that challenge. Okay, welcome back. So first of all, we're more complete so that we can run backwards, so that we can run forwards, we can walk forwards, we can run left, we can run right, and we can have an idle animation in the middle. Now, if we were to do that, we would find that we end up with a kind of cross formation, and at these points in between, it wouldn't really know or behave very well. So what we're actually going to do is tweak these axes so that we get something a little bit different. Instead of having right and forward, we're going to end up with having the angle and having the speed as the other dimension. So that if we want to go backwards, you need to turn around 180 degrees on your angle and go at full speed. So what should these values be? Well, these should be a little bit different. We're going to go from -180 to +180 on the angle, full circle. And speed-wise, we're going to go from 0 to, I don't know, let's say 100 for now. And then how would we be laying out these different animations that we've just laid out in one way? We can lay them out differently. We've got a backwards animation that's going to go at full speed at -180. It's also going to go at full speed at +180. So that backwards animation needs to be in 2 places. So let's find our walk for backwards and put it in this other place as well. Now our walking right, that's going to go, actually that's a walking left animation, that should go over at our -180. Our walking right should go over at our +180. Out in one, to go from the behave very well. So what we're actually going to do is, and having the speed -180 to +180, and with animation that's going to go at full speed. And then how would we be laying out these different animations that we've just laid out in one way? We can lay them out differently. We've got a backwards animation that's going to go at full speed at -180. It's also going to go at full speed at +180. So that backwards animation needs to be in 2 places. So let's find our walk for backwards and put it in this other place as well. Now our walking right, that's going to go, actually that's a walking left animation, that should go over at our -180. Our walking right should go over at our +180, and our full walk should go there in the middle. And as I said, we do need some sort of idle animation, so let's go and look for the idle combat animation. Has the, actually that's a walking left animation, that should go over at our -180. Our walking right should go over at our +180, and our full walk should go there in the middle. And as I said, we do need some sort of idle animation. So let's go and look for the idle combat animation. Has the gun raised, I believe. So we go and put idle combat, and we're going to put idle combat all the way along the bottom here in each one of these slots to make the blend super clear that no matter what angle you're at, if you're idle, you want to be stationary. So let's try that. I can now move my angle. You can see I start moving at a different angle depending on where I bring that green nub in. And if I come down, you can see it reduces my speed until I am idle. So that's what it's doing no matter where I start, and I come up and it starts to move me over to the left or to the right or wherever I am. It is kind of making sense. So my challenge to you is to complete this blend space. We're going to do that by adding jog combat animations so that we can go faster as well as slower. And where should they go in our scheme? Whereabouts should they be put on this blend space? Pause the video and have a go at that challenge. Okay, welcome back. So first of all, we're going to want to move down probably these blend spaces here, the walk left, the walk forward and right, because we're going to want the jog animations to go at faster speed at the top. Then we're going to go ahead and look for our jog, and we're going to look for, it should be, some of them are jog combat, I believe. Let's try and find them somewhere in here. Here we go. There's a whole section down below. The combat comes at the end, so it's not very easy to search for, unfortunately. But if we go and look for it, we should have a jog forward combat. There you go. Put that in the middle. We're going to need a jog backward combat. Where is that? Jog backward combat. That's going to go over to the right and the left. Full right, full left. And we're going to need a left. So jog left combat's going at minus 180. Or minus 90 in actual fact, and the jog right combat is going at plus 90. And I just noticed I left a gap here where we had our walk backwards. So let's find walk, right mouse button, backwards over here, and now we should be able to blend between these guys fairly accurately. So going backwards, jogging to the left, walking to the left. My only problem appears to be that my idle animation has got all of this kind of looking to the left and looking to the right business going on, and if I go anywhere in between with this interpolation, it kind of goes a bit frenetic. So what I want to do here is actually find a different idle animation. I've used the wrong one. So if we go, it's not idle combat that I want, but rather I think there's an idle ability right mouse button, which is more static. So we'll go and bring that in over the top, which replaces, we bring it over the top of those idle points on our combat space. And now you can see if I bring that green nubbin around, you can see we don't have any of that frenetic moving around. We've just got a very nice blend space that smoothly blends between our walk animations, our stopped animations, and our running animations in any direction. And that hopefully gives you an idea of why blend spaces are just so awesome at doing things like locomotion. And by the way, it can be helpful to enable the labels in this view so that you can see what the names of the animations are at the various points on this blend space. In the next lecture, we're going to look at bringing this blend space into our animation blueprint and how to hook it all up. See you there. Hello and welcome. In this lecture, we are going to be learning how to connect up our animations to our gameplay, and we're going to get the speed of our character hooked up to the blend space so that we can get this effect. Let's dive in and see how it's done. Okay, so we have got ourselves a blend space to integrate into this ABP shooter character. First thing I'm going to do is I'm going to go ahead and delete these two blends that we use as an example of how the animation blueprint animgraph works. And instead, we're going to bring in from the asset browser in the bottom right the blend space that we've just created, this BS_locomotion. If you drag that into your anim graph, you'll see it brings in this little green node here. And very much like the other blend nodes and things like that, we've got ourselves an anim pose that we can drag into our output. And if I hit compile, you can see it's just in our default space. And then you can see this little visualization, which is quite handy, of the little blend space, and we could go ahead and change the values in here statically, or we could input some variables into here. Well, we're probably going to want to do the latter, so I'm going to go ahead and delete the two variables we've got, the left and the forward, because we know now that what we want is an angle, which is going to be a float. So let's change that over to float. And we're going to need a speed variable as well, which is also a float. And we can patch those two in, the speed variable into the speed. the angle into the angle, and we go hit compile, look at our anim preview editor, and just tweak the values. So first of all, the speed, let's bring the speed up a little bit. Let's bring the speed up to about 30. See what happens. There you go. He starts to walk. If I bring it up to 70, he is getting closer to running. I bring it to 100, or not 10, 100, then he's full on running. And then we can change the angle. So at 90 degrees, he's going 90 to the right, minus 90, he's going over to the left. We can go somewhere in between, so we can say 45 degrees. You can see he runs at a 45-degree angle, and you can see the blend space where it is trying to pick in the blend space and what animations it's sort of blending between. It's blending between the forward animation and that 90 degrees right animation. So that's cool. We've got that going, but as we know, this needs to be driven by our actual gameplay. And why do we do that anyway? Why don't we just have the animations drive our gameplay, saying, you know, we need to be moving forward at such and such a pace? Well, the reason for not doing that, the reason for not using the animation to drive gameplay, is that you often want your designer to be able to tweak all sorts of variables about your gameplay. You want them to be able to say, okay, well, it doesn't feel right that this character is running at this speed. It needs to be running at this speed instead. And walking should be more at this speed. So you don't want your animations to constrain the design and game feel. You want the animations to come off the back of your game feel and make it look good. So during your design process, you might realize, actually, we need a faster running animation, and that's okay, but you want to be able to change up the game first to get there, rather than have to go and try and record a different running animation or find a different running animation, and then these two times when things really must line up with the animations, but this is not one of them. So there are exceptions to every rule, so don't take this as a completely set in stone rule. You'll definitely see instances of games that drive some features from the animation and update the set. How do we do this? Basically, the mechanics of it are that this blueprint, this animation blueprint, has an event graph like other blueprints do, which means that it can have things like a tick event. If I go over into the event graph and have a look, we have got a couple of event nodes in here that we can use to start from. We've got this blueprint update animation. If we come off of this, every time it wants to update the animation, it's going to give us the execution node and allow us to go ahead and grab some state. So what we're going to do is every time this is called, we go and grab some state, and notice here it's got this get pawn owner. That's saying go ahead and get the pawn object. So let's remind ourselves the pawn in this case is a character being a subclass of pawn, and it would be this BP shooter character. Why would it be the BP shooter character? Well, let's see. Because this character, if we select the mesh, go to the viewport, it's currently running just a simple animation, but what we want to do is change the animation mode over to use animation blueprint, and we want to use that ABP shooter character. So that is why this is the pawn owner. It's using that animation blueprint, so the blueprint now has a pawn owner. And so what we want to do in this update function, just to summarize, is we want to grab the information from the pawn about its movement. We want to say, what's your speed? What's the angle of your movement? That's what we're going to calculate. In this lecture, we're just going to do the speed because it's the simplest to do. The angle is going to require a little bit of manipulation with transforms, which we're going to look at in the next lecture. So the node that we're going to want here is to get the velocity of our pawn owner. That gives us this vector here. And then off the back of that vector, we want to find its magnitude or its length. So we can drag off that vector, search for the magnitude, and notice it's been clever here, and I've searched for magnitude, but it's given me the function called vector length. So clearly magnitude, they've clocked that it's a synonym for vector length. Why do we want to get the vector length rather than the vector itself? Because we're looking for a float, which is the speed. Vectors include the direction as well as the speed, which we're going to need to calculate the angle, but it isn't what we need to calculate the speed. So a little mini challenge for you here. Go ahead, there isn't any other challenge in this lecture. Go ahead and set the speed using this vector length. And remember, if you need any execution pin, we're trying to do this on the blueprint update animation. So pause the video and have a go. Okay, welcome back. So the speed is what we want to set. So if I drag that into the blueprint and hit set speed, you can see we've got an execution pin that we need. We're going to get that from the blueprint update animation. And we need the data pin, which is going to be the speed that comes from our vector length of getting our velocity. So we should be able to go ahead and save and compile that. You can see that's reset the speed to 0 because now it's trying to set it from a pawn owner that is not really there. So what we're going to want to do is actually go ahead and play in the world and see what we've got. Okay, this is much better. We've got ourselves a pawn that's staying static on the ground, except for when I move, at which point it is giving me some speed. And if you use an analog input, such as a controller, you can see that by changing the analog input, that sort of changes the speed, we can change how fast this guy is moving. Now, obviously, there are two problems here. The first one being that if I move off at an angle, it's just using the absolute speed, so it's not adjusting that angle in our blend space, and so the animation looks wrong. The other problem is that we're getting definitely some foot sliding here because the speed of our animation is not matching the speed of the character in our game. That's something that we will look at fixing in a following lecture as well. Great stuff. Hopefully you now understand how animations should hook up to gameplay using the animation blueprint, and you should be able to go and apply that to your own game. See you in the next lecture where we will be hooking up those angles so that this movement looks a bit more natural. Hello and welcome. In this lecture we are going to be sorting out the angle of our blend space, hooking that up to our gameplay, and in the process we're going to have to learn a lot of maths, a lot of transforms and vectors. So let's dive in and figure out how that works. Okay, so we want to be able to get the angle at which we should be moving. However, before we do that, we need to do a little bit of maths because we want to understand how we can get this angle which is local to the player, and I'll explain what I mean by local and global, and how we can get that from a global velocity and what those terms mean anyway. So let's have a look. First of all, we need to have a bit of a basic primer on transforms and what transforms are. We've seen them, or you will have seen them a little bit before when you look at any of the scene components. That's these ones in the hierarchy. You can see they have a transform here. It's the location, rotation, and scale properties. That's basically what a transform is. But one thing that you're not seeing here is that also part of this transform is the fact that these scene components are in a hierarchy, meaning that the transform also has a parent, or, they're basically hierarchical. So how does that work? Well, here's a kind of toy example. We've got the cube here, which say is our base. It's the center of our world or something. So that's going to be our world space. We've got this character here, the little smiley face, and he's got a position in the world relative to his home base. And then this character has a gun, and the gun has a position relative to the character. So the way this hierarchy works is that the parent of the gun is the character, the parent of the character is his home base or the world. And then we have some local coordinate systems within these. So the world's coordinate system is the world system, the global system. Then the coordinates of our character are then local to its position. So the gun is positioned relative to its character. What does that mean? That means that if the character decides to go off on a little escapade, then the gun moves with it, because the position of the gun relative to the character has remained the same, but because the character's moved, its position in the world has moved. Same happens with rotation. If the character turns around, the gun must turn around as well. That's how transforms work, essentially. There's also scale, but we're not going to look at scale. It's the same, but it's just complicating things, and we don't need to have a look at that. It's not relevant to us. So let's have a different look at this. We've got global space and local space. So the global space has the base at the center of the world, and the character has gone off and to the right. The center of this is what we mean when we talk about transforming between global and moving locally, just because it gives us the gun location vector. And if you transform a position vector, now vector, that position doesn't really get updated. Instead, the vector gets rotated and scaled because we're dealing with a velocity out of the way. Let's go ahead and calculate our direction from this velocity. So we know the velocity is in global space, and we want to convert it to local space. Now, that means that, generally speaking, we're always trying to do things the other way around, usually, because we're saying, well, we've got the position, the local position of a gun, its local transform. We want to figure out what it is in world space so that we can render it relative to everything else. Now, that's not what we're trying to do here. We're trying to do the opposite. So what we actually want is called an inverse transform. The transform goes this way from local to global. The inverse transform goes from global to local. So because we've got this global velocity, we want to inverse transform. So let's take off here and look for inverse transform. And you can see that we've got these two options. We don't care about these matrix ones. We've got the two options for direction and location. And as I said, the difference is that a location will move that position around. The direction's just going to apply the rotation and scale. So we want the direction. We need a transform to rotate it by. We're going to have to get that transform of the pawn itself, of the character. Where is that pawn in the world? So let's go ahead and grab off the pawn owner and look for the transform property. Get actor transform, that would be the one. We'll pipe that into our inverse transform direction. And we've got ourselves a new vector out of this. So the next step would be to get the rotation of this vector. So we're going to look for rotation, see what we can find. We've got find look rotation, make rotation on axes, to quaternion. No. Let's have a look at rotation from X vector. If you read the documentation here, it says it's going to set the yaw and pitch from this vector, but it won't set the roll because it can't get that information from a vector. That's fine. We don't care about the roll. In this case, all we care about is the yaw because we want to see how far we're turning to the right or left. So rotation from X vector, that's the one that we want. It's going to return us a rotator. And for us to get just the yaw from that rotator, we're going to right-click on the pin and hit split struct pin, which goes ahead and splits that struct into the roll, pitch, and yaw. You can do that on a vector as well, by the way, I think. You can right-click and let's see. I think I'd have to break the link to do it, so I'm not going to show you. But basically, we've now got our yaw here, and that's what we want to set. So again, mini challenge. Set up the yaw to be the angle and test it out. So again, mini challenge, set up the yaw to be our angle variable that goes into the blend space and test it out. Try it out in the game and see if you're able to run around successfully. Okay, welcome back. So we're going to drag in again our angle variable, set angle. Going to set the angle from the yaw, and we're going to get the execution pin from the end of speed. Compile and save that, and we're going to go over to the sandbox and hit play. And now let's try moving around. A controller would be ideal so you can test out the different gradients and the nuances, and sure enough, you can see if I start moving around now, I'm able to move backwards, I'm able to move forwards, sprinting, and sideways, and 45 degrees. All of that works based on the maths that we've calculated to calculate our angle. Great stuff. So we've learned a lot about transforms and vectors and how you can transform vectors, both inverse and forward transforming. And in the next lecture, we're going to look at fixing this foot sliding that we are seeing here. I'll see you there. Welcome. In this lecture we are going to get our foot sliding in order. As you can see now, if I'm walking, my feet are no longer sliding, and if I'm running, the same, I'm also not sliding. So let's dive in and see how we can do this by calculating the speed of our animations. So let's try and fix this foot sliding issue. If I'm moving especially visible at a slow walking speed, you can see he's basically running across the ground. Now, why is this happening? The reason this is happening is that in our blend space locomotion, we have got some speeds set up here, and these don't actually correspond to the speeds of our animation. So what we're saying is that in gameplay we're moving at 100 centimeters a second. It's going to be playing this running animation, and if this running animation is faster than 100 centimeters per second, you're going to get foot sliding. Also, if it's slower, you're going to get foot sliding. In both cases, you'll get foot sliding. So what we want to do is match up these axes to actually play the correct animation at the correct speed and then interpolate when we're at a different speed. Obviously, this is going to mean that there is a limitation on our gameplay. We can't go faster than our maximum animation will allow because we are unable to display that. But if you did want to do that and you did want to go faster, then you would have to get more animations and so on. But as I said, that allows our designer to change up the gameplay first, and then we can go and hunt for animations if it works. So let's have a look at this run animation. How can we calculate the speed of this run animation? It's not automatically told to us by Unreal, so there's a little bit of maths involved to get there. Let's go and find the jog forward animation, and we want the jog forward combat in particular. Here it is. And how do we go ahead and get this? Let's just pause the playing of the animation. What we want to see essentially is how fast one of these feet moves across the floor. So from the point it touches down to the point that it is starting to leave the floor, we want to know how fast it moved across the ground, and that is the speed of our animation. To do that, we're going to track the speed of the ankle bone. So if I click into the world, you can see I should be able to select the foot_R. As of Unreal 5, you're no longer able to actually click into the viewport to select the bone, so what you'll have to do is go over into the skeleton tab over in the left and use the search bar to search for this bone. And that is our ankle bone, and as we move across you can see that it is moving the rotation, but notice it's not changing the location. Why is that? Because the location shown here is a local location rather, and that location is relative to the knee, and it's not actually moving relative to the knee, it's only rotating relative to the knee. So that's why we are getting that. If we switch over to the world location and go ahead and move now, you can definitely see that we're getting movements in our location. So we need to switch over to world for this calculation to work. And then we want to find 2 points. The point at which we land, we're going to want to find out the Y value. Why the Y value? Because that is this axis here that we're looking at from left to right. It's the Y axis. You can see it in the widget at the bottom left of your viewport. So we're going to want to find the Y value when we hit the floor. We're also going to want to find the time at which we hit the floor, which is this second number in brackets on our timeline, the 0.19. And we're going to then go and look and find the second time, which is where we're going to leave the floor, find that time, find the Y value. And then we're going to apply this formula here. Let me break it down. The first thing is to calculate the foot speed, we need to calculate the Y at the finish minus the Y at the start. We want to divide that by the time at the finish divided by the time at the start. So I'm going to work through this calculation with you. All you're going to need is somewhere to capture the numbers, such as a new notepad, or I'm going to use a new text document in Visual Studio Code, just an untitled one. I don't need to save it or anything. And I'm going to open up a calculator on Windows. It's just easier to do it on your computer because you can copy and paste into it. And we're going to start finding some values. First of all, we want to find where do we hit the floor, about here, which is going to be a time 0.16. Let's type that into our text document. 1.16. There we go. like that. And what's the Y value? Best to capture it now because it's going to be hard to find later. It is, let's just go ahead and copy it because it's hard to see at my screen resolution, 17 point something. Cool. Now that's the start. Where is the finish? Let's go and drag the foot across. Around here is probably where we're leaving the ground, and it is conveniently 0.30. And the Y is going to be a negative number now, -28 point. There you go. So let's apply our formula. First of all, it's the finish that we want in there first, not the start, counterintuitively. We're going to subtract the start, like that. It's going to give us a negative number of, that's how far we moved. 45 centimeters is how far that foot moved in one stride. Now, how long did it take for that to happen? First of all, let's get that number down in our file, in our text file, and see how long it took. Let's clear and start with the finish, and then subtract the start. Gives us this number, which I'm going to copy with just Control-C on Windows. Without selecting anything, it just automatically copies the number that's there. And then we're going to want to work out what this is equal to. So let's clear and start with the -45 and divide by the 0.14. Enter gives us this number right here, like that. So this is telling us that our jog speed, it's giving us a negative number because that's kind of going backwards, but the jog speed forwards essentially is going to be 325 approximately centimeters per second. So that's what we're going to want to have in our blend space. So we now need to do the same thing for our walking animation. So that's going to be a challenge for you to calculate the walk speed as well as the run speed. Find the walking animation that's relevant, probably the forward one, and apply the formula and do it the same as we just did. Finding the foot speed is Y finish minus Y start divided by T finish minus T start. Challenge for approximately centimeters per second. So that's what we're going to want to have in our blend space. So we now need to do the same thing for our walking animation. So that's going to be a challenge for you to calculate the... We want to find, first of all, our blend space and see what animation we were using. Value, like that. World, we've already distance, sort of. And first of all, calculate the finish time. So clear this, finish our 30. Our blend space, that wasn't part of your minus, well, basically 130 wasn't part of your challenge, but we're going to do this now. Let's open up our blend space location because these divisions aren't so easy for us to do that. Well, the first thing is that we don't need to get things exactly 100% right, but the second thing is that we can change the divisions or the number of divisions on our speed axis. So the way I'm going to do this is I'm going to round these two values to approximately the nearest 50 and use 50 divisions. So what we'd have here is this one's going to round up to 350, this one's going to round up to 150, and then what we can do is figure out how many divisions we need. So 350 divided by 50 is going to give us 7. So let's go to our speed, add in 7 divisions, add the maximum axis value to be 350, like so. And now what we should get is at the 350 mark, we are going to be running. When we're down at 150, we are going to be walking. So if we save and then anywhere in between, obviously it's going to interpolate as best it can. Now let's go ahead and play and see if that's between, obviously it's going to interpolate as best. Best it can. Now, let's go ahead and play and see if that's helped fix our foot sliding issue. Let's look down at the ground so we can see our feet. As I am walking, you can see we've got far less, if no, foot sliding whatsoever. As we run, it's certainly no noticeable foot sliding now. So I'm quite happy that we've successfully calculated a decent approximation for the speed of our animations. And hopefully you can apply this to any animations that you use in the future if you're trying to put them in a blend space or match them up to our foot movement. So that concludes our little foray into animation for now. I think we've got a good starting point for our animation with a third-person character. The next thing that's really missing here is some gun architecture. So we're going to look at how you architect guns for third-person and first-person shooters in the next lecture. See you there. Hello and welcome. In this lecture we're going to create a gun. And we're going to learn how we're going to be architecting guns for this game so that they are swappable, so that we can have different properties on different types of guns, and that's generally how the architectures work in shooters, first person or third. Let's dive in and see how it's done. Okay, so we haven't checked in on our project plan in a little while.
Greystone is a melee fighter who never backs down from a challenge. An incredibly durable, skilled swordsman, Greystone takes the fight to his enemies and is capable of fighting even when his enemies can't. Focus on buying cards that increase your physical damage and attack speed. Greystone excels in combat. Make Way is a powerful ability that will deal damage in a vortex around you. Use this to engage enemies or to quickly clear minion waves. Assault the Gates allows Greystone to take the fight to his enemies, leaping to target areas and dealing damage. This ability allows him to engage, disengage, and even traverse terrain. Stoic will allow you to take hits better, granting you passive armor and health, making you more durable in team fights. And finally, your
Hello guys, welcome back to another video. For creating a character, and just go sci-fi characters in here, so we'll check all those out. Yeah, then we have this, I'm not sure what you would call this, but next up, sort of this samurai design, really cool hat there with feathers and design for him. Has like a moth-tailed Muriel, Kalari, that's how you say it. So you'll see a lot of the characters on here have crystal fit to characters is to take part of the character models and export them to Blender and take some of the models like
Kwong is a durable fighter that excels at initiating fights. A master swordsman, Kwong can utilize his legendary blade to change how and where he uses his abilities. Focus on buying cards that increase your physical damage and health, and reduce your cooldowns. Judgment of the Heavens will have Kwong throw his sword to a target location. If the sword lands on an enemy hero, they will be tethered to the sword for a short time. Keep in mind, if you aren't holding your blade, you cannot attack, so reactivate the ability to draw your sword back. Gift of the Heavens is an aura around the sword that grants Kwong and nearby allies lifesteal on basic attacks and abilities. Light of the Heavens will call lightning down to the blade, dealing damage in an area and granting Kwong bonus physical and energy armor for a short time. If Kwong uses Judgment of the Heavens, lightning will strike the sword. And finally, your ultimate is Fury of the Heavens. Kwong will wind up and deal damage in an area around him, slowing enemies. However, if his sword is out, Kwong will teleport to his blade, wherever it is in the world, then deal damage. When playing Kwong, utilize your legendary blade to approach engagements on your own terms. Use Judgment of the Heavens to isolate and lock targets in place. This is especially useful when comboed with allied AoE abilities and ultimates. If you need to get back into the fight, use Fury of the Heavens to teleport back to your sword and catch enemies off guard. Kalari is a high-risk, high-reward melee assassin, adept at mobility and stealth. Kalari is more mechanically demanding and requires a kill to make a clean escape. Focus on buying cards that increase your physical damage and health. Play safe and look to gank enemies that are pushed too far forward. If Kalari gets a kill, her Shadow Walk will reset, so utilize this as often as you can. Do not engage enemies head-on. Kalari is best at stalking enemies that are out of position. To make the most of her potential, you'll have to land Blood Dagger and Death sentence to secure kills. Consider saving backflip in case you miss. Pick and choose your moments. You are capable of dealing a ton of damage, but so are your enemies. Always look to flank and be a threat the enemy team has to be conscious of.
where have we got to? The player movement is done. The animation, for now, is done. And the shooting, that is the next thing for us to focus on. Now, it's a little confusing here because our mesh already appears to have a gun. But actually, we don't want to use this gun. We want to use it in a different way. Reason being, in a shooter type of game, you often want to be able to architect to the character. It's a rocket launcher or a shotgun or a mesh. That would work, except that then we lose the modularity that allows us to add multiple components to the gun. So what we really want to do is go down the route of having an actor for the gun that is childed to the shooter character. Now, this is something we haven't come across before, but it works like this. You can have a shooter character and a gun as its child, and the shooter character can have multiple components which are childed to each other. So you've got the capsule, we've got the mesh as a child of the capsule at the moment. And the components of the gun can be childed to that. So the mesh gets childed to the mesh of the character, and if it's got any other components, such as maybe a particle effect at the muzzle of the gun, that might be childed to the mesh. So you can see that these hierarchies are kind of independent, that you've got the scene components, the ones that have transforms, over on the right, and they can be in a certain hierarchy. And then the actor hierarchy actually follows the hierarchy of the scene components. The actors don't have a hierarchy of their own. This is the bit that takes hierarchy of actors to relate to each other. But they are gun actor, and in this case, it's not going to be a pawn or character or anything like that. It's just going to be a straightforward actor, because we don't need any behavior, we don't need to possess it, we don't need to do anything. It's just a simple actor. So let's go ahead and do that. In fact, a little challenge for you. Go ahead and create that C++ actor, something you should be able to do. Little mini challenge. Attempt it. Okay, and back in. I'm going to go and do it. New C++ class. And we don't need to have, let's see, actor. That's the one we want to choose. And we're going to go ahead and call this one gun. Simple as. Let's create that class. Okay, and once that's done, it's going to pop up in your code editor, and we don't need to do anything with it just yet, because the first thing I want to do is create a blueprint subclass. So right-click on your class in the content browser, and instead of calling it my gun, I don't know why it automatically defaults that, BP underscore gun. I'm going to put it in the root of content for now. We can do a bit of reorganizing once we've got more classes, as I've said before. We'll create the blueprint class. As you can see, it's completely empty. It's got this default scene root. We're going to want to fix that up. What we want to do is actually add a component in C++, because this is a C++ course. Let's practice the muscle of adding components in C++. It also means that we're going to have access to those components from within our C++ code to manipulate and write our code there. Now, the setup we're going to want is to have a scene root component, which is just going to be a scene component, and then a mesh that's a child of that. Why do we want that? Because we want to be able to change the position of the mesh relative to the root of the gun, so that we can basically place the handle in different locations for different meshes. So if we have different guns, we can make sure they all have the handle in the same place, so that when we attach it to the character's hand, it's going to appear with the handle in the character's hand. Okay, so how we're going to do that, we're going to go over to our Visual Studio Code, and I'm going to create a private section down here where we're going to store the U properties for the different components that we're going to come up with. So I'm going to create a U property, visible anywhere. We want our components to be visible anywhere because they're pointers. We don't want to be able to edit the pointers, but we do want to be able to see the properties of those pointers and be able to edit those. And that then becomes the purview of the class that we're pointing to. That then decides what gets shown, what is editable. So all we want to say here is that it's not the pointer that is editable. So that's why we're going for visible anyway. Anyway, a little bit of revision there. Now we want this to be a U because it's a component, then it's a scene component that we're wanting. Type it correctly, scene component, and it's a pointer to it, and this is going to be our root component, like so. And then we're going to want a U property, again, visible anywhere, for our mesh. Now, the class for the mesh is going to be a U static mesh component, because this isn't a skeletal mesh, it's rigid, it doesn't have any skeleton, any bones, so I want that to be a pointer, and this we're just going to call the mesh, like so. In fact, I think I need to be a little bit careful here because I think root component already exists in the parent class for actor, so I'm just going to call this root instead. And then we've already got a constructor over in the C++. We're just going to need to include the appropriate header files here. Now, a little trick when you're in Visual Studio Code is to find out where a constructor. I think I need to be a little bit careful here because I think root component already exists in the parent class for act. You're going to search for, in this case, we want to know the static mesh, so static mesh component, and we can see that the static mesh component.h, if I go ahead and open it up and hover over the tab, you can see that it is under this long path, but the bit that's interesting is that it's under classes, which then we can look up from there. It's going to be components, static mesh component. So I can close that tab down, and just above our include, in fact below the include for our gun, we're going to do a hash include for the components, and then the static mesh component. Now, actually, I've just remembered that the meshes that we've got, for some reason, aren't actually static meshes. I believe they might be skeletal meshes. You can find this out by going into the asset packs, shooter game, weapons, and having a look at these meshes. And sure enough, if you hover over them, you can see that they are skeletal meshes. Don't ask me why. For some reason, that's what they are. So we're going to want to change the type to skeletal mesh in the header file. So instead of the uStatic mesh, it's going to be uSkeletal mesh instead. And same for the include, it's going to be the skeletal mesh component.h that we want. Remember, there's no u in the header files. And I believe the scene components is already included here by default. So it's time for a challenge to add a mesh component of your own. We're going to create a root scene component, set it to the root, and set it to the root for the class, and create a mesh component and set up the attachment between the two so that the mesh component is a child of that root scene component. Pause the video and have a go. Okay, welcome back. So we're going to go over and set, first of all, our root. It's going to be a create default sub-object of type uScene component, and then we are going to give it a name, which is going to be with the text macro. We're going to call it the root and finish off with a semicolon. Then we're going to set it as the root, so set root component, we'll set it as the root component for the actor, so set root as the root component. Good stuff. Then we're going to want to create our mesh, so mesh equals create default sub-object, and it's the uSkeletal mesh component that we want as the class, and then the text macro for, just going to call it mesh, and add a semicolon on the end there. Then we want to set up attachment, so it's going to be mesh arrow setup attachment, and we're going to want to attach to the root like so. Cool stuff. So we can go ahead and save that and hopefully compile and build, and we'll go over into Unreal and have a look at our child class. And sure enough, in here we've got ourselves the root, we've got the sub mesh, we've also got this default scene root which is hanging around. I think let's restart the editor and see if that just goes away. Sometimes when adding components, things can linger around like that and get cached. And sure enough, if we open up the BP gun blueprint again, you can see that we've just got those two components we've added, the root and the mesh, and we probably want to go ahead and change out the mesh for one of the skeletal meshes from the asset packs from the shooter game. We've got right default sub-object. object. Of type sub mesh. We've also got this default scene root which is hanging around. I think let's restart the editor and see if that just goes away. Sometimes when adding components, things can linger around like that and get cached. And sure enough, if we open up the BP gun blueprint again, you can see that we've just got those two components we've added, the root and the mesh, and we probably want to go ahead and change out the mesh for one of the skeletal meshes from the asset packs from the shooter game. We've got a rifle, we've got a launcher. I'm going to choose this one to be the rifle. So actually calling it a BP gun is a little bit disingenuous. This should probably be the BP rifle. So let's go ahead and rename that. Go over to the content browser and rename it to BP rifle. Or BP gun underscore rifle. No, we'll call it BP rifle directly. There you go. And that has given us a gun. Now, obviously, now this means that we can have all sorts of properties against this actor, such as the strength of the weapon, its range, and so on and so forth, by creating new properties in C++. And that is the strength of having this architecture, is that the guns can then be a little bit different. We can have different shooting mechanics for rifles versus snipers versus RPGs, things like that. So that's great, and we can also have different stats. So we can have a strong rifle and a weak rifle, depending on different blueprint subclasses. Cool stuff. Now, in the next lecture, we're going to look at how we're going to actually spawn this gun as a child of our current character. I'll see you there. Hello and welcome. In this lecture, we are going to be spawning our rifle at runtime from our character class in C++. Let's dive in and see how it's done. Okay, so we want to get our gun spawning as a child of the shooter character. The first point of call is to be able to spawn that actor from within another actor. We're going to do this at runtime. We're going to do it at begin play because that's the way you kind of need to do it. When you're spawning actors, you need to do it at runtime. And the way we're going to do this is we're going to get hold of the world first, so get world. And then we're going to call a function on get world. By the way, world and level are synonyms, so what we're actually doing here is we're going up to the level and saying, hey level, can you create us an actor? Because all actors essentially belong or live in a level. So we're saying, you know, spawn actor for me, please. And this is a spawn actor that takes a template. You can say, I want this actor that I'm going to spawn to be of type a gun. And for that to work, we're going to need to have an include up here hash, include for the gun.h. And then we're going to take in an argument, and the argument to spawn is actually can be a class type. So by default, it will go ahead and spawn the C++, but here we want to spawn the blueprint child of this gun. So we need to figure out what that's going to be. That needs to be hooked up in Blueprint. It can't be hooked up here in C++, at least not easily. The best place to do it is in Blueprint. So we're going to do an Alt-O to go to the header file for our shooter character, and we're going to add in a new U property here to allow us to configure the class that we should be pointing to in order to spawn an actor. Which Blueprint class should we be spawning from this shooter character? We're going to have it as an edit defaults only. Why edit defaults only? Because we don't want to be able to edit this at runtime, because it would give a false impression that you can change what type of gun we're using at runtime, whereas begin play's already been called, that gun's already been spawned, and so it wouldn't actually update anything. So we don't want to make it editable to not give people a false impression of what can be done. Actually, don't child of this gun. So we need to figure out what that's going to be. That needs to be hooked up in Blueprint. It can't be hooked up here in C++, at least not easily. The best place to do it is in Blueprint. So we're going to do an Alt-O to go to the header file for our shooter character, and we're going to add in a new U property here to allow us to configure the class that we should be pointing to in order to spawn an actor. Which Blueprint class should we be spawning from this shooter character? We're going to have it as an edit defaults only. Why edit defaults only? Because we don't want to be able to edit this at runtime, because it would give a false impression that you can change what type of gun we're using at runtime, whereas begin play's already been called, that gun's already been spawned, and so it wouldn't actually update anything. So we don't want to make it editable to not give people a false impression of what can be done. And then here we're going to use a macro called T_subclass of, which you may or may not have come across before. And T_subclass of is a template, so we use these angle brackets again, and we want it to say a subclass of gun. And basically what this means is that it allows Blueprint to restrict the classes that we can select from to only the classes that are subclasses of the gun C++ class. Now, this isn't going to be a pointer, because we're not pointing to an actual instance of the gun. What we're getting here in this variable is a class itself. In this case, it's a Blueprint class, but it's still a class. So what we're going to want to call this is the gun class, just to make it super clear that this is not actually the gun itself. We do want another U property here to store the gun, and that is going to be not an edit default, so basically we don't want to make this a visible property at all, but it's going to be an A gun pointer. See the difference? One of them is a T subclass of gun, the other one is a gun pointer, and this one is the actual gun. That's once we've created an instance of the class, that's where we're going to store it. So let's go on over into our shooter CPP and finish off this begin play where we are spawning things. So we're going to have gun equal to get world spawn actor gun, and the argument we're going to pass in here is the gun class, which we're going to be setting over in Blueprint. So let's go and try and compile this. It may give us some errors. Let's see. I'll have the message log open with the compile log, and sure enough, we're getting some errors over here in the header file saying undeclared identifier. It's because we need to forward declare the gun. So I'm just going to do this at the top because it's in two places. I'm going to say class a gun, like so. And just a reminder, forward declaring like this means that we can keep our compile times down by not including too much in the heavy header files. Let's try recompile and see. Looks like that was the only error. It's now compiled successfully. Let's go ahead and hit play and see what happens. Exit, have a look at we basically want to have a look at the message log, which I don't have open. So let's go to Window and Developer Tools and have a look at the output log and see if we have any errors here. Yes, spawn actor failed because no class was specified. Sure, no class was specified because we didn't configure it yet in Blueprint. So this I'm going to give as a challenge to you to hook up the gun, find the property in our character blueprints, set it to the correct gun, and test that it spawns. Pause the video and have a go. Okay, welcome back. So let's go over to our shooter character. EP. And find the property, which should be on the root or the class defaults. Go into details, and under shooter character, you can see we've got our rotation rate here, which we have configured. And we have got our gun class, which is a drop-down, which allows me to choose between the gun, being the C++ gun, and here's where our naming convention comes in handy. The things prefixed with BP underscore are the blueprints. So we want our BP underscore rifle. Go ahead and select that, compile, save, go over into the scene and hit play. Now, hopefully we have not got any errors about spawning our gun. The gun should have spawned okay. And to find out if it has, we can F8 and have a look in the world outliner. If I make the world outliner a little bit bigger, I can search for the BP underscore rifle. Hooray, we've got a BP underscore rifle. The moment it's in the middle of nowhere and it's not correctly childed, that's going to be the subject of the next lecture. So I will see you there. Hello and welcome. In this lecture we are going to be covering lots of cool things, but most importantly we're going to be looking at how we can child a actor to another actor. As you can see here, the rifle is a child of the shooter character, and how we can make it such that the mesh there is actually attached to the hand of this skeletal mesh. As you can see, that gun is moving around with that player's hand. Let's dive in and see how it's done. So the first thing we want to do before putting our gun in the hands of this mesh is we want to remove or hide the gun that is currently there. Now, I find that the easiest way of doing this is to hide the bone that has the gun mesh. Let's have a look. So if we go over to the shooter character, BP would be a good entry point for this, and then I want to go to the actual mesh. Here we've got the skeletal mesh, and if I go to the skeleton, then we can find that this gun here, if I click on the gun, has got a bone leading up to it called the weapon bone. And weapon underscore R, and basically we want to hide this, but the easiest way to hide this across the board is going to be to do it in code, and we're going to do it in C++. So the first thing is to get hold of the mesh component. The way to do this when you're on a character subclass is to call to getMesh. Cool. So we've got getMesh. Then with the mesh, we want to hide the bone. There is handily a hideBoneByName method, and this actually exists on the parent of the skeletal mesh component, the skinned mesh component. Let's have a look at the header file briefly. Skinned mesh component.h. There is a couple of functions here. The one we're looking for is hideBoneByName. So you can see the signature here. We've got the bone name comes in, an fname, and then the second thing is this eFizzBodyOp. Now, as far as I can tell, this isn't used in the code base, but we've got to provide it because it's there in the signature. So let's go ahead and use it. So arrow, going to do the hideBoneByName. Unfortunately, my autocomplete's not working. That's a bug in 4.25 at the moment in VS Code. Autocomplete doesn't 100% want to work, but that's okay. We can learn to do it the manual way instead. Then we're going to want the name of the bone, and I'll leave that up to you as an exercise to fill that out in a second. And then the second thing is we wanted that fizz op body thing. We're just going to go for, that's an enum, so we're going to need to fill it out. I'm going to use F12 to go to the definition and see what we have got. PBO none, don't do anything. That sounds like a sensible default. Let's go with that. And then we'll use the semicolon to finish off our line right there. So let's compile this and see if we've got all the includes we need. Cool, looks like it's working, so we must have all the includes we need. Now, what's your challenge is to put in the bone name. Give that a sensible default. Let's go with that. And then we'll use the semicolon to finish off our line right there. So let's compile this and see if we've got all the includes we need. Cool, looks like it's working, so we must have all the includes we need. Now, what's your challenge is to put in the bone name. Give that a quick go, mini challenge, and we're coming back. The bone name is weapon_R. It was hinted at a little bit before. Weapon_R should do the trick. If we go ahead and recompile with that now, and we hit play, you can see that he's no longer holding a gun. Fantastic. So the next thing is to put a different gun in his hand, the actor gun. So we need to go over to our skeleton, and what we want to do here is add in a new socket. So we're going to add in a socket in place of our weapon R. And what is a socket? A socket, as it sounds like a plug socket, is something that you can plug in. It's a point at which you can plug in other things. So you might want to be able to plug in, for example, a gun, and you want it to be childed not to the mesh as a whole, but to a specific bone of that mesh, which means that it'll move correctly with the character's arms when he's doing an animation, when he's jogging around. It's going to look like it's attached to his hand rather than somewhere on it, not rigidly fixed to his torso. So we're going to add a child socket to a weapon R. To do this, you go to the skeleton, you right click on the bone that you want to attach this socket to, and you click add socket, and we're just going to call this one the weapon socket. I'm using camel case here as my convention, and that's what we're going to want to attach to. Now you'll see where this comes in handy when we go to actually do the attachment for our gun. Now, the thing to note here is that we don't want to do a setup attachment as we would do in the constructor. At runtime, when we do attachment, we have to use a different set of functions rather than the ones we use in the constructor. And remember when I said that the only hierarchy here really is between scene components. Now, fortunately, we don't have to go in and get the root component of the gun and attach it. There is a helper method on the actor that allows us to do attachment, and that is attach to component. So let's see where that's defined. If we go to look at the actor.h header file, and there's a couple of these. We want the one that lives under game framework, and we're going to go and search in here for attach to component, open brackets, and find the actual declaration. Here it is. So what's this going to take in? It's going to take in a uScene component, the parent that we want to attach to. In this case, it's going to be our skeletal mesh of the character. The transform rules, we'll get to this in just a second, and then, there you go, the socket name. That's where on a skeletal mesh should we attach to. If it's a skeletal mesh, it'll attach to the socket. If it is not a skeletal mesh, it'll ignore the socket argument and just attach if it's a static mesh, for example. So we want to attach to get mesh. We have these transform rules. What are those? Let's click through F12 to click through to the different rules that are available. These are the preset rules. You can define your own, but you might as well use these preset ones. We've got keep relative transform, keep world transform, snap to target not including scale. We'll ignore these last two. The main two to look out for are these first two, and it basically means when we're attaching, should it stay the same place it was in the world, or should we use that world position as the new local position? In our case, because we want that gun to essentially be at 0, 0, which would be its location in the world, we want to keep the relative transform. So let's do that. We're going to have the F transform rules, keep relative transform. So F transform rules, colon, colon, and then it should be, let me see, just copy over the keep relative transforms, like so. And then we want the socket. So again, text macro here, and then the socket name, which was weapon socket. And finish off the line. That's going to set up the attachment. And now the final point is going to be we want to set up the gun to have this class as its owner. This is a bit of a subtle point. Why do we have an owner? I just said that there wasn't any hierarchy between actors. Well, there isn't in the sense of transforms, but they do have ownership. And where this ownership really comes into play is in multiplayer and in damage. So we'll see later on how we will need to know about the owner. It also allows the gun to know what is the owning character, and it can use that to get references to the owning character. Later on, this will be useful. At the moment, we don't particularly care, but we're just going to do it for completeness sake. Now, I actually named this wrong. It shouldn't be set up owner, but set owner to this, because this is the actor that is the owner of the gun. Cool beans. Let's compile and see if this is working. Compiled successful. Let's dive in and play the game. Awesome. We have got a weapon in our hands. Is it in the right place? Let's have a look. Let's F8 out of here and have a look at the hand. Not quite. You can see that we could do a little bit of adjusting here. So that's what we're going to do. And this is a challenge for you. Basically, what you're going to try and do is find what the offset should be on the mesh such that this handle is actually inside our mesh's Wraith character's hand. Pause the video and have a go at that. Okay, welcome back. So I'm going to do this by selecting that mesh and trying to move it. I'm going to have to set the grid snap size in the viewport to a little bit less, and I'm going to try and zoom in as best I can on that hand. Okay, bringing that down a little bit. I think that's a good shout. Now let's go ahead and copy the location and open up, go to the content browser and open up the BP rifle. Open the full blueprint editor, go to the mesh and stop simulating and paste the location that we had copied in there. Okay, cool, copy that and let's go and hit play. And let's see that it actually brought across the right thing. F8 out and zoom in. By the way, you can use the scroll wheel to slow down your movement when you're moving in this kind of way. Fantastic. Looks like he has got his hand directly on the handle. Awesome stuff. So we have learnt how we can child actors to other actors and how we can attach. And zoom in. By the way, you can use the scroll wheel to slow down your movement when you're moving in this kind of way. Wraith character's hand. Viewport to a little bit less. I think that's a good shout. Now let's go ahead and copy the location and open up, go to the content browser and open up the BP rifle. Open the full blueprint editor, go to the mesh and stop simulating and paste the location that we had copied in there. Okay, cool, copy that and let's go and hit play. And let's see that it actually brought across the right thing. F8 out and zoom in. By the way, you can use the scroll wheel to slow down your movement when you're moving in this kind of way. Fantastic. Looks like he has got his hand directly on the handle. Awesome stuff. So we have learnt how we can child actors to other actors and how we can attach scene components to sockets of skeletal meshes. In the next lecture, we're going to be looking a little bit at shooting and how this gun architecture basically dovetails into a shooting architecture. So I'll see you there. Hello and welcome. In this lecture we're going to be architecting our gun such that when we hit the mouse button or the trigger, then we are going to get a log message, and this log message is the first step in getting many other things running off the back of this gun architecture. Let's dive in and see how it's done. So we want this gun ultimately to be able to shoot, and that is the core of it. Why are we choosing to have the gun as the core of our shooting architecture? Well, as I've already alluded to a little bit, we want to be able to support different types of methods of shooting. Now, what are the kinds of methods of shooting that we can typically have? There is direct fire, which often uses ray tracing and direct line of sight to ascertain whether or not a victim has been hit. So it would go and say, okay, I can see that enemy, it's that line of sight from the gun to the enemy is clear, it hits him, so we have to do him damage. Otherwise, if I missed and I didn't hit the enemy, it doesn't do damage. That's one very easy way. It doesn't really replicate the physics of a bullet, but there's no need to. So for performance reasons, we don't. Now, with a rocket launcher or something like that, it's often a very slow projectile. We want to see the effect of that projectile moving through the air, and the time delay can be important, in which case we might spawn that projectile and see whether the projectile hits in 5 seconds time. Or we might go down a different route with bullet drop and rifles and sniper rifles over long distances. So all of this could change depending on the implementation of our gun. Now we're going to implement one gun during this section. It's going to be a rifle, a direct shooting type of gun. But in order to leave that architecture open for you to extend, we are going to make the gun responsible for doing shooting. So that means we have to go ahead and introduce some shooting architecture into our gun. So we've got a gun.h. We want to create a public function to this that is going to allow us to essentially pull the trigger on the gun from the shooter character or from wherever we're binding input. In the case of the enemy, for example, we're going to be pulling that trigger from the AI. So let's go ahead and create a void. It doesn't have to have a return type, pull trigger method. And it doesn't need to take anything. All we need to know is that we want to pull the trigger in this frame. So having that is sufficient. Now I'm going to go ahead and create the implementation with Control-Shift-P and create implementation. And then in here, all I'm going to do is I'm going to put a UE log, and I'm just going to make it warning to stand out and change the message to you've been shot, like that. And that's great. So that's what we're going to call in our character.cpp. So this is going to be a challenge to you. It is some more input binding. We've done lots of input binding here. You've got lots of examples of input binding. Go ahead and do this to hook up a shoot action. You're going to have to create a new action in the project settings for shooting. Bind that to your key, your right trigger, whatever you want to bind it to. Then bind it in the character, set up player input component method to do this, and then after binding the character you should be able to call the pull trigger from within the function that you have created on the character. Remember to put a function in to character in order to set up the bind. binding rather than trying to bind directly to that gun. Binding directly to the gun isn't going to work. You need to put a little function intermediary in there. So pause the video and I'll give you a little bit of a hint or a little bit of a start if you're struggling with that last part of the challenge of creating the intermediary function. Okay, so here comes the hint. If you don't want the hint, pause now. But the hint is going to be, we're going to do something like this, which is to have a new private function called void shoot and create the implementation over in C++. And it's going to be in here that we call to the gun's own method. So the gun's pull trigger, we're going to do gun and then call pull trigger on that. From within shoot, and this is what you need to bind. Okay, so pause the video again if that's where you want to take things, and then let's go and set up the actions. Okay, so we're going to go over to our project settings. So settings, project settings, and we want to dock this and go to our input, and we want to add a new action, and we're going to call it shoot. And then we're going to bind this to the left mouse button and the right trigger, not the right trigger axis, the right just trigger. Thought that's what I'd selected, but I had not. Okay, so we're binding to both controller and mouse, and then we're going to go over and bind the axis in our shooter character CPP. So copy this bind axis for jump. I mean action, of course. I'm always going to get those two mixed up. We'll switch over to the shoot axis here. The pressed is what we want, and instead of binding to jump, we're going to bind to a character shoot instead, like so. And let's go ahead and build. Okay, it looks like that has succeeded. Let's close that on down and see if it works. So let's exit the game and hit play again and have a look at our output log crucially. Hit play. Yay! So if I hit the mouse button, it is working. Let's see if the same thing happens if I use my right trigger. Yep, right trigger is working too for firing. So obviously a log message is not the best way of letting your player know that something is going on in the game. So in the next lecture, we're going to look at adding in particle effects to do just that. I'll see you there. Hello and welcome. In this lecture we're going to be looking at spawning a muzzle flash so that when we hit the trigger we get a particle effect. So let's dive in and see how we can do this from C++. Spawning a muzzle flash. So that when we hit the trigger, we get a particle effect. So let's dive in and see how we can do this from C++. Okay, so we want some particle effects to spawn from the muzzle of our gun. What's going to be the best way to do this? We're going to first of all have a look at what particle effects we've got available here. I've taken the ones from the shooter game. Obviously you can use any particle effects that you want. You can find them on the asset store. You can take them from example projects like I have. We want to go under the effects, so asset pack, shooter game, effects, and then look at particle systems, weapons, assault rifle, and I'm looking for the muzzle one at least initially, and we want this assault rifle MF. And you should be able to see it's going to take a little bit of time to get the shaders in here compiling, but this is what essentially the muzzle flash looks like. It looks like a muzzle flash, so that's what we're going to be using. And we're going to try and spawn this in C++ when we have the trigger pulled. So let's go over into our gun. I'm going to go to the gun CPP, and instead of this log message of having been shot, not particularly useful, we want to spawn a particle effect. And to do this, we're going to be using a function from the gameplaystatics.h. So let's go over to the gameplaystatics.h and have a little look. In here, we want to spawn an emitter, they're calling it, spawn an emitter, and you will see, if we have a look at this, that what it's taking in is a world context object, it's taking in a particle system, which is the emitter template, as they're calling it, the location, rotation, scale, blah, 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 or alternatively, I think you can make it attached, so we can do a spawn emitter attached, and this is going to try and attach it to a component, so we can see that this takes in a scene component to attach to. Now in this case I think this is what we want. It depends on the particle effect in question, but some particle effects are going to keep spawning particles for a duration of time, so you want those particles to keep coming out of the muzzle of the gun. As the gun moves, they might be creating some smoke, some stuff like that. If you move your gun while you're shooting, you want the particle effect to move with it. And as it needs to attach to, so any kind of offset. So let's have a look at that. If I go and open up all, you know, we've mentioned that this is a skeletal mesh. So I'm going to go and find that rifle in the content browser and open up the rifle mesh. And what you'll see over in the left, if you have the skeleton tree pane visible, then you're going to see that we've got this rifle root, we've got the rifle magazine, which presumably can be swapped out or something, but we don't particularly interested in that. And then there's this muzzle flash socket. So that's where we're going to spawn our muzzle flash. If it didn't have, or your mesh doesn't have this, then you can go ahead and add one, because we can always add sockets in the way we've seen in previous lectures. So let's have a go at spawning this. The first thing we're going to need is one of these particle system references, and the best way to do that, again the best way that I know how, is to create a uProperty and do it in Blueprint. There are other ways you can do it by named references, but I really don't like using named references. They break easily if you rename stuff, so much easier to do it in Blueprint where all of that is handled for you. I'm going to make this a uProperty, edit defaults, or actually this could be edit anywhere. Why? Because if we were to change this during gameplay, which you might want to do if you're trying to tweak things and say, oh, well, does this particle effect look better than this one, then this would actually work. The next time you shoot, a different particle effect would be created. And then the type of this needs to be a uParticle system pointer, which we're going to call our muzzle flash, like that. And that's what we're going to be setting up over in Blueprint. And let's go back into our pull trigger method in C++, and we want to call it that uGameplayStatics function. So uGameplayStatics. Notice it's not auto-completing here because I need hash include for this. If I hover over that gameplay statics, you can see that it's under engine classes Kismet gameplay statics. So all we need to do is Kismet gameplay statics.h, and we should have uGameplay statics to auto-complete from, and we want to spawn, and this may or may not work because of the version I'm in Unreal. We want to spawn the emitter attached, and we want this muzzle flash right here, and we want to attach it to a scene component. In this case we want to attach it to our gun's mesh, and we want to attach it to the appropriate socket, which again I'll let you fill out, is the, go over to the gun, it's the muzzle flash socket. I'm going to copy it from there directly and just put a semicolon on the end of the line to top it off. So this should work. Let's go over and hit compile in the engine. And once that's finished compiling, we can go over into our BP_rifle, open the full blueprint editor. I just prefer to deal with that, and look at our, let's see, if we go to the root, in fact the actor itself or the class defaults, go to the details pane, you can see we've got this muzzle flash property, the new one, and we need to find a particle effect in here. I'm going to look for the keyword muzzle. Let's see. Maybe muzzle was not the one we were looking for. It's assault rifle MF, I think. So muzzle flash is what it's standing for. So assault rifle MF. That's the one we want. Compile and save that, and we go over into our sandbox and hit play, and see if shooting indeed launches up our muzzle flash. And you can see that it is continuously shooting at the moment. So we do want it to just be a single muzzle flash. So I think I'll actually choose a different muzzle flash. I think I'll use the one from the Wraith asset pack, which here we've got sniper and primary. I'm going to choose the primary, just because I'm not wanting to create a rapid fire weapon. That's a slightly different way of doing things. Not massively different, just more of a kind of, once you're holding, you start the emitter, and once you are finished with it, you want to close it down. In our case, we just want to launch that emitter one time. So we're going to do Alt-P again, and see if we, there we go, now we shoot, we get a single flash of the muzzle, and if everything's hunky-dory, it seems to be attached nicely to the end of the gun as well. As I move around, wherever I move around, whichever way I face, the muzzle flash is in the right direction. Cool, well this is really starting to look more like a shooter game with particle effects. So in the next lecture, we're going to look at the first steps of ray tracing, which will be actually to go and reach up to our character owner for some information. I will see you there. Hello and welcome. In this lecture we are going to be seeing things from the player's point of view. We will be getting hold of the player's viewport, the location and rotation of the camera essentially, so that when we hit the trigger button we can draw a debug camera, these little red guys here, these little red boxy cameras that show us where that viewport is, and we can confirm that we can then use that later on for ray tracing for the gun. Let's dive in and see all of that in action. Let me start this lecture with a question. So if you are aiming through your viewport like this, and you're trying to line up the center of your screen with that D on D command center or 0 command center, whatever that's meant to be, and I aim, what would I expect to hit? You might say, well, I'd expect it to hit that 0, Sam. That seems like the obvious answer. Well, that's not necessarily what you are going to hit, depending on how you do things, how you do your raycasting. So let's have a look at the strategies we have for raycasting. The most obvious is you say, well, we're firing out of the gun, so we're going to raycast down the barrel of the gun. Oh, by the way, this setup, which is very, very crude, is basically our third-person setup. We've got a camera back here, we've got the character, we've got the gun, and he's trying to shoot at another target character over here. So, well, first of all, we raycast out of the gun, like that. Pew! Maybe it misses, because our camera is not pointing where the gun is pointing, not necessarily. Even though they might be pointing in the same direction, they're slightly offset from each other. So they won't, it's more natural in third-person games, aim down. And so that's what... Now, fortunately, there's a way for us to get this rotation, funnily enough, I believe, or draw debug helpers. That's the one. And if we go and have a look at this one, F12 to go navigate to a header file, if you've already got it in your includes, we're going to look for one called camera. Draw debug camera, and this draws something that looks a little bit like my diagram here, a little bit of a triangle or a frustum that we can use. So what's it going to take in? It's going to take in the world, a location of that camera, a rotation for said camera. So location, rotation, field of view, we'll set that probably to a default like 90 degrees. There's a scale. There's a color defaults. These are all defaulted, so we can just use their defaults. So let's try. Draw a debug camera down here in my gun, and we'll put it in the pull trigger method, because that's why we're doing our work. It needs, first of all, what was it? It was a UWorld. So we get our world that we need to draw into. The next thing would be a location. Let's just get actor location for the time being, and do a get actor rotation as well. And then what was the final thing that we needed was a field of view. Let's just go for a 90-degree field of view, which is just a random thing there. And we can go ahead and compile and see whether this shows up. And then let's hit play and hit the trigger button. I'm not seeing anything here. Let's do an F8 and see if we can get closer. Still not showing any kind of camera in here. I'm wondering if it's really, really small. So one of the other options here is that we might want to have persistent lines. And so that means we need to specify everything up to it in C++. So we can set our scale to 1. We could even increase it maybe to a scale of 2, just in case it's the size that's a problem. We can choose a color that's more visible, maybe red, so F color : red. And then we can try having persistent lines be true, and try that one out for size. So compiling again, and jumping into play, and there we go. We hit the trigger, and you can see that it shows up a little camera box here where we hit trigger, and its rotation and location are set by the gun's location and rotation. So now we want to try and get the viewport instead. So as I've already said, this is going to be on our controller. So let's look at controller.h. Again, we want the one in the game framework, and we're going to look for viewport in here. Beg your pardon, actually viewpoint is the word we're looking for. And there's a few here. Get actor eyes viewpoint. That would be looking through the actor's eyes. But we actually want the get player viewpoint, which for an AI controller will use their eyes, but for a player will use the player's camera. So that's what we want. We want the get player viewpoint. But first of all, we have to get hold of that controller in the first place. And the way to do that is, first of all, we need to get our owner. Remember that when we had our shooter character CPP open and we go down to, or go up to our begin play, you can see we're setting the gun's owner to be the character. That means that in the gun, we can go the other way. We can say get owner, and that's going to get us the shooter character. Now, it's not going to know that it's a shooter character. All it knows is that it is an actor. So we're going to have to do a cast here. So we do a cast to the A shooter character. And in fact, we don't even need to know anything as much as the fact that it's a shooter character. It's sufficient to know that it is a pawn, and any pawn can then possess this gun, even if it's not a shooter character. So try and be as non-specific as possible. Why does it need to be a pawn, though? It needs to be a pawn because we need to get a controller, and only pawns can be possessed by controllers. So let's put this in a variable. It's going to be a pawn star, and then owner pawn is going to be the name of the variable. Then we need to check that this is not null. And I'm just going to do this with a one-liner that says, if it is null, we return early from our pull trigger, so that we don't have any risk of trying to call anything with a null pointer. So then we can do a pawn owner get controller, and we want to save that into the A controller star, and this can be the owner controller, like so. And again, we want to just check that this isn't null because we're going to be calling a method on that, and we can't call methods on null pointers. It makes Unreal unhappy and crash. So this is where we can now do our owner controller, and we should be able to call to that get player viewpoint. So here comes the challenge for you to set that location and rotation using that new function. You can see the signature for it. Again, we go to controller.h header file and look at that get player viewpoint. Try and see if from this signature you can work out how to use it to get that location and rotation that we want to pass into our draw debug helper. And so you're going to remember that this is using out parameters, so revise your out parameters. Draw the debug camera using that snippet that we've just written and test it in the viewport. Go and click the trigger button a few times in different locations and see where that camera ends up showing. Pause the video and have a go. Okay, well, Welcome back. So get player viewpoint, I'm going to copy the name of the method and bring it over here. Because it's an out parameter, I will need to declare first the variables that I want those values to go into. We've got an f vector location. We have got an f rotator rotation. And we want to pass those in as the arguments. Let me just fix up my indentation there a little bit. And we're going to pass in the location, the rotation, and we know that because it's just been declared here, when reading this we can guess that these are now out parameters, even though there isn't any syntax helpfulness from C++ on that regard. And then we can pass this location instead of the actor location, and we can pass this rotation instead of the actor rotation into our draw debug camera. And we can go ahead, complete let's action from where I was just looking, so you can just imagine how we're going to be able to shoot a ray out of that camera, down the end of the camera, and try and hit something over there that I was looking at the time. And that's what we're going to be doing in the next lecture. See you there. Hello and welcome. In this lecture we're going to be getting some line tracing set up. It's